Good afternoon, everyone. I'm delighted to introduce our next speakers. From GHD, Dr. Paul Espy, and from SSEN Transmission, Dr. Lisa Woolhouse. Paul is the Technical Director for GHD Energy, has over 20 years' experience supporting clients with renewable, feasibility, transmission planning, investments and policy studies. He also leads GHD's PLEXOS work on constraint modelling, aiding prospects in the UK, Middle East and Australia. Lisa is Head of Transition at SSEN Transmission, an LSE graduate with PhD in Energy Economics. She has extensive experience in energy markets regulation and network development. She has worked with regulators, developers, OFTOs and supported SSEN Transmission on various network developments. Lisa leads the SSEN Transmission Energy Transition Strategy. Together, Paul and Lisa will be sharing strategical planning transmission network, driving transparency and insight with PLEXOS. Please join me in welcoming Paul and Lisa to the stage.
Thanks for sticking around. This is hopefully be quite interesting. I think what's really noticeable that when I did my PhD in economic and energy modelling, you'd have to use a laptop the size of a small child and leave it to run for about a day and a half to get anywhere. And, you know, now we're talking, it's so much more sophisticated, so much more fun. So, you know, you're in the right space. So what I want to talk to you a little bit about today is strategically planning the transmission network in the north of Scotland and how we're thinking about and how we're starting to do that with PLEXOS. And it's quite a different level of detail, if you like, in particular the network that we're looking at doing with PLEXOS. So we are actually stretching its legs quite hard with Paul's help. So what we're going to do is just quickly run you through the challenge that we've got in the north of Scotland. It was one of the slides this morning in the very first presentation that showed that amalgamation of all those different challenges that led to the sharks. We are a microcosm of all those different challenges on quite a stringy network. So it's how we're developing PLEXOS to do that. And we'll talk you through a few of really probably more how we're developing our study to think about how we're approaching it, and some of the insights that we've got from it in our fairly early stages of development and what we're going to be doing next with it. So I think of it as a slightly different application of PLEXOS perhaps than you've seen today. So, our challenge, well, I think that it's really summed in that chart on the right. What we've got connected to our network at the moment is the light blue stuff. What wants to connect to our network is the dark blue stuff. And that's a range of solar, even in the north of Scotland. It's quite astonishing to me. The wind, I understand it, it's really windy. Some of our wind farms on the Scottish Islands are running at over 50% capacity factor. You know, they're as good as offshore, but there's not quite as much space onshore. Lots of offshore wind looking to connect, quite deep, some of it in floating technology. So we've got the will they, won't they kind of thing about that. Quite a lot of batteries and long duration storage as well. In addition, what we've got on what was really quite an outer reach, if you like, of the UK's network is this really increasing interest in this large demand growth. So there's the data centres, there's potential hydrogen because of all the renewables up there, and there's even the decarbonisation of oil and gas platforms, which always makes me chuckle, but there you go. So it's quite a complex tapestry that we're trying to look at. Now, to date, how we've planned it, now we're a TO, and that differs from quite a lot of how it works in Europe and other jurisdictions. So the NESO that you've heard talk quite a lot about today, they're the GB's system operator. They strategically plan a multi-vector energy system, if you like. So they're looking at initially electricity, but they're going to be looking at gas and hydrogen as well. They look at those really quite high-level strategic boundaries. We as TO go really deep into the network. So our role is a little bit different, but do we need to do strategic planning? Well, the way that we've done things before is really react to customer requests, right? So customer wants to connect to our network, they apply to do so, then we are obliged to give them a connection offer, which means basically do some system modeling to see how they can connect, what the point of connection would be, what the impact on that local area is. So we spend a lot of our time, as you can see, doing a lot of system planning for the connection, essentially, of that gazillion megawatts of pipeline. Now, the conundrum that we've got, and I think this is quite common across much of Europe and other jurisdictions as well, like Australia, is that we can't connect everyone that wants to connect to our network. There's no way we need 100 gigawatts of generation in the north of Scotland, but we should connect what needs to be connected, right? So it's a kind of change in approach from being very reactive and doing millions of connection requests to start to think a bit more strategically with trying to align with what the NESO is doing. Say, okay, what could the role of the north of Scotland be in this energy transition, given the fact that we've got this really deep base of renewable generation, obviously apart from solar, that is there, runs at pretty high capacity factors, and could potentially be a relatively lower cost addition to the GB's energy mix. It's fair to say, and I think this has been mentioned earlier as well, is that the regulatory background has always been, don't build it very big because they might not turn up. That's really changing now as we move away from that kind of, well, renewables might not turn up. And we're now saying, look, there's millions of them. They want to come. So we need to now do some forward thinking about what we actually need on the network. In addition to that, we've had some really interesting shake-ups in our market. We've had a reform of this kind of queue of connections. So if you look at all those dark blue bars there, the connections reform piece of work has said, right, who's ready to connect by 2030 then? Seriously, are you ready? Have you got planning permission? Have you got a connection offer before 2030? Can you really connect? So it's starting to try and shake up that queue for 2030. There's also, as I said, been this change in anticipatory investment. It used to be filthy, dirty words you could never say to the regulator. They're now quite open. Instead, we build it bigger. Well, you never used to want us to. No, do, build it bigger. So there's quite a big change in the whole underlying mood music as well. And this leads to the first panel discussion this morning around that. We need to do some more actual centralized strategic planning of our network. So that's our challenge. What we're doing is we're developing a network plan for 2030, in brackets, and beyond. I just couldn't fit it on there. Because for us as a business, if we are developing our network out to 2030 with connections reform and so on, what happens after then? You know, or we're not going to connect everything that wants to connect, everything that needs to connect by then. So what do we do? What do we do beyond 2030? Us as an asset owner and an asset builder and an asset maintainer, we need to know what we're going to be doing, what our investment plan is for the longer term, and how we can kind of optimally develop our own network. We are liaising closely with the national, with the NESO, the National System Energy Operator. Sorry, that changes names occasionally. So there we are. We're stuck with NESO. That's great. So because they're doing their strategic spatial plan, and you've heard about the high transmission boundary modelling that they're doing. What we want to do is to complement that with a more detailed look into our network. And so that the NESO then gets a better understanding of what's going on deeper into the network, not just on those really main transmission boundaries, because that gives you a high-level view of what's going on. It doesn't give you that deeper view of where they're connecting. What are those more localized constraints looking like? So, what are we doing to address the challenges? Thinking about how we more strategically plan a more detailed network. So that's in our area, that's right down to 132. We also look at 275, 400, and HVDC. We're getting an increasing amount now of HVDC connections on a relatively small network. Super challenging from an operability perspective, as you can imagine. Most of our connections and system planning, not kind of strategic system planning, but that connections modeling system planning. We've done it with the, with silent, quite detailed power factory modeling for your network analysis. The key issue for us as TOs in this world of strategic planning is we're not planning for that certainty of connection going forward. We need to think about that whole what-ifery. So what if that connects there? What if that offshore wind farm that might be contracted for 2035 doesn't turn up? What if we get some hydrogen over there? What are those impacts deeper into our network? And we also need a lot of comfort. If we've always done things in silent, right? Our network engineers need the comfort that we're not just pressing a button on a PLEXOS box. We know what the network looks like in that box. We know how it works. We know what it's doing across our network. And that for us is a really key thing, because we as TOs, we are working closely with the NESO, but we also need to retain that ability to challenge, to question, because they're coming up with decisions that fundamentally affect our assets. So we need to retain that ability to challenge the NESO and to provide it with this better detailed information to feed into its own strategic planning. I say the ability of PLEXOS to be able to interact with our silent models through script and so on is important to us as well. Really important is using the tool to better understand the impact on our actual assets. Now, we've come up, as part of the work that we've been doing with GHD, is some really just interesting findings. For example, on a transformer with a couple of large batteries located on it, the number of tap changes that is happening, we usually say 5,000 and then 5-year, a refurb of those. These are now happening within a matter of 6 months. That's a huge change in how our assets are being used, and we need to understand that. We need to feed that into more strategic planning, because those costs are kind of hidden, hidden kind of battery cost, if you like, that it could do with being better understood. So we're working with GHD to develop a pretty detailed PLEXOS, quite nerdy model of the north of Scotland. And I think at that point, Paul, you can nerd out.
Well, you were talking about tap changes so well there, I thought you just wanted to carry on. Right, thanks everyone. So basically, what we've been doing for SSE is really to try and come up with a fairly granular transmission system model in PLEXOS that builds on some earlier work that we did for them on Shetland. And really, the challenge here is, and we had wrestled with this at the start, was how detailed do we go? So where we've landed at the minute, as you can see, the diagram on the right-hand side there shows all the sort of nodes that we're considering were actually within the PLEXOS model. So basically, we've modeled all 132, 220, 275, and 400 substations. We've got 70 grid supply points. We've got about 500 individual generator units actually modeled in there, and depending on what year we're looking at, we've got potentially 6 HVDC links from remote islands, but also some of the other ones that go across the sort of national boundaries. To build a model, obviously we need data to go into it. So one of the things we have is hourly time series data for offshore wind, for different renewable profiles, as well as GSP demand profiles. So these are based on historical data. So these are actual recorded wind farm power outputs, generator profiles for other renewables, as well as GSP demand profiles. So they're sort of time series aligned. We've also got to model some power flow controllers. So we've got HVDC controls, as well as AC power flow controllers modeled with some constraint equations. And if we have enough time, we can go on and talk about those. And also we can't just do SSC on its own. Obviously, we need to have some representation of the network below theirs, which is Scottish Power, and ultimately for National Grid network as well. To develop the model, we've also used Energy Exemplar's GB PLEXOS model, so that becomes the sort of balancing node when we're looking at our future scenarios, our sensitivity cases for the sort of different generation capacities that Lisa showed were in the queue earlier on. So what does it look like? Bit of a mess, possibly, but what we tried to do here is really set this out on the right-hand side, not expecting anyone to look at the detail. The key takeaways from it, though, are this network model lines quite well with the power factory model. So the blue lines you can see there are 400 kV lines, red is 275, black is 132, and there are also some HVDC in there as well. So what we've been doing is doing some targeted ST runs to look at power flows over individual transmission circuits across key GB transmission boundaries, but also within particular boundaries. That's given us insights in terms of the balance between HVDC and AC power flows, asset utilization levels through GSPs, including potential reverse power flows. We're also looking at contingencies in terms of double circuit transmission outages, impacts on unserved energy, as well as generation constraints. The model's been the advantage of having a very detailed model is we can put end dates in, so we can put decommissioning dates for individual assets, and as we go further out, we're able to see the impact of these falling off or potentially being extended in terms of if the asset lifetime can be extended. The beauty of this model is it does align. It's not 100% representation of the power factory model, but it's probably about 90% of it, and that means that in essence, the data that comes into it in terms of the circuit ratings, the transformer ratings, all that underlying data is already aligned and ready for the more detailed model, which is obviously still needed to support stability analysis, voltage, reactive power flows, which you're clearly not going to get from PLEXOS. In addition to the ST runs, we're also doing some long-term runs to complement targeted ST runs with using the LT functionality within PLEXOS to look at beyond 2035, in terms of what network capacity might be needed, giving PLEXOS the build options and the costs to look and see what might be needed for different scenarios, but also then looking at giving PLEXOS the renewables as locations to see where does it think the optimal locations would be for renewable generation. And similarly on the latter point there, we've heard about demand earlier on about data centers. That's also a feature of a lot of the inquiries within SSE network. So again, part of that strategic what-if analysis is giving PLEXOS the option, say, where does the program, where does the software think it should be built? The key thing here is we're overlaying the ST with the LT. So it's not about trying to get the perfect answer or the perfect decision. It's trying to gain the insights from targeted ST with LT, finding the overlap, finding the common projects, and understanding the sensitivities. So in terms of the boundaries, again, this one's a little bit detailed for all the power system engineers. So basically, this example on the right just shows the Northern Scotland B0 boundary. But for context, there's a number of parallel 132, 275, and 400 kV lines. There's also some various HVDCs that cross the wider GB boundary. So as part of our modelling, we've had to look at power flow control on the AC lines, flow control on the HVDC, which has been informed by targeted power factory studies in order to get the balance right. Ultimately, it needs a different mix of different flow controls. So DC can obviously have flow control within PLEXOS, but also constraint equations. I think that came up earlier on. So at the end of the day, there is a need to look at constraint equations in order to make sure the total flow, whether it's forward or backwards, depending on where the direction is, but that meets the sort of engineering basis that goes in to support some of the other work in the national strategies and documents. We're currently working to get that calibration right. We've done some initial runs and fair to say a bit more to do perhaps on that one there. But again, it's trying to get it so it's reasonably well coordinated with the power factory model. We might need to think quite inventively about how we do all that flow control because currently PLEXOS doesn't quite have all the functionality you would perhaps want to match perhaps with something like a PSSE or a power factory. So there's a few learnings that we're picking up as we go along in terms of how best to do that. But with the granular model, we can look at different outages, N-1, N-2, N-D. So again, we're going through using a combination of the inbuilt functions, but also targeted modeling in order to give some further insight into perhaps outages which maybe in the past maybe wouldn't have been considered double circuit outages. But I think we heard earlier on about I think Paul mentioned about the black swans and the maybe it should be black sharks, I don't know, the multitude of them that have come up in the last period. So maybe what planning standards used to consider as not probable actually now is becoming more probable, and therefore it's important, to try and understand the impacts of that. So that's the sort of one of the examples there. Lisa very eloquently talked through the tap changer problem earlier on. So basically, as Lisa says there, some of the batteries and other embedded generation on the network is causing transformer tap changes to move a lot more than has been done previously. We've been able to take the power flow, the time series data from PLEXOS, run it back through Power Factory to understand the movements over a period of time, and that can then go into inform sort of O&M strategies in terms of where there might be increased maintenance. That's just one little snippet. There's a lot more that can be done with that information, but we just thought it was an important additional benefit from a sort of O&M perspective that we can actually gain from the modelling. Right, how do we bring everything together? So as I said, basically we're trying to blend ST runs with the LT runs together in order to sort of sit these together to get the key learnings and outcomes from that. So as I say, we're looking at LT runs to do targeted optimization, location, and capacity for renewables, as well as optimizing network reinforcement. We then overlay these with the targeted ST runs, which have a sort of heuristic-led view as what future projects might be, and then bring those together to say, okay, where's the overlap? Where are the common projects? Where are the ones that depend on particular scenarios? Where are the ones that might only occur in particular circumstances? And also, the importance of the LT is, as engineers, it's sometimes easy to look at things and say, you can't build that there. There's no space in the substation, you'll never get planning consent. Part of the value in using PLEXOS to do some of the LT works is to say, if it comes up with a really good solution, maybe we need to look again at that. Maybe we need to challenge the preconceptions around you can't build there or come up with an innovative solution and perhaps use the software to perhaps give a bit more insight to some of that what-if analysis, maybe where further thoughts might be needed. As part of this, obviously, as Lisa says, we're bringing the results together, which ultimately will help as a business SSE form their strategies, what their future workload and investments might be, but also to help with engagement with stakeholders, including the NESO, where this detailed modelling can actually then be used to actually better inform maybe some of the optioneering, as Lisa says, challenge and perhaps the stakeholder engagements for communities, for councils as well, about where things might need to be built in the future. So basically, to conclude, the modelling we've done in PLEXOS, I think, has been done in such a way that we have some comfort in terms of what the modelling is, what it's coming out with in terms of results. We're still working on the journey, so at the end of the day, there's still a bit of a lack of transparency in some areas, but we're working with Energy Exemplar in order to understand what more we can gain from the tool in terms of the decision making, the things that go into the PLEXOS decision. So that'll be helpful as well to get that to sit side by side with the engineering understanding, and hopefully they broadly align. Allows us to tackle the key what-if questions in terms of generation, demand, network build, certainly going past 2035 where it's a lot more uncertain. And it allows us to sort of think through that push and pull between sort of heuristic, engineering-led, gut feel decisions in terms of what might be needed for a network, as well as the precision in terms of very detailed constraint calculations. So in terms of the next steps, we are looking to do a bit more work on the power flow control and the AC-DC balance. We're also looking to map that graphic that I showed you earlier on with the dig silent one in terms of the coordinates, so they will look really the same, and we can use the dig silent one to refresh the PLEXOS one. We do need an enduring approach to data transfer, which is something we need to look at in terms of how we're doing it. We're aware of a lot of the functionality, the cloud API and things like that we can use, and that's something that we're still investigating. Other things in terms of renewables, hydro and pump storage, a bit more to do. Same with batteries. We do need to have a look at the impact of those, but that's stuff that we'll get into in the near future.
Yep, thanks, Paul. And I think just to sum up, really, it's quite a novel and slightly radical use of PLEXOS, I think, to go really deep into this network. But for us as TO, it's really important that we do that, because I think what is a little bit the danger, and having worked with energy models for more time than I care to think about, is there is that little bit of danger to press the button and just go, that's the right answer, without then asking why. Why is it doing that? Why can't I see that? And so it's actually challenging the model as well to stretch its legs so we better understand what it's doing. Because I do worry a little bit about, PLEXOS is a hugely valuable tool. It's enormously powerful. But that black boxery, as well as the what-ifery, mustn't run away together, because they don't make very good couple. So it's good to know what's going on. So thank you.
Yeah, thank you.
Thank you. We've got time for a couple of questions for the break. I know Paul and Lisa are sticking around for a few days, so you can go.
Thank you. Nenad Jovanovic from McDonald. So since we have two doctors on the stage, hopefully we're going to get a pill or a vaccine for all these problems, but let's see. You mentioned you're going to keep going, and as you have mentioned previously in your question, it's not the real world in modeling. So you go down to 135, 30 something kV. So I guess you're going to go deep down, because in some cases we're going to have distributed generation coming up to the distribution level. So good luck with that. When you get infeasibilities with Xcelerate and with PSSC, because it's a non-convex model, because we know AC/DC doesn't work always perfectly. But my question to you, when you go further on, how deep down you're planning to go, and when it's the boundary, do you say, okay, enough is enough?
Yeah.
And what I understood, you're not going to model like all the I wouldn't call them zombie projects, but like lots of projects. I guess that you're going to cost optimal LT solution, and then you're putting into detailed modeling.
Yeah, so basically a couple of things there. Yeah, 132 is pretty much where we're at. There's already more than enough detail in there without going any further. In terms of the generation, something that big pipeline that's there, what we're doing is for the sort of near term 2030, it's really informed by, it's probably fairly clear where most projects are perhaps going to go, but maybe there's questions around timing. For later on, clearly there's a lot more uncertainty. Lisa mentioned about, will some of the offshore wind farms turn up or will they not? So what we're doing is we're giving PLEXOS a bit of a helping hand to say, well, it can't literally all just connect anywhere. There still needs to be a bit of rationale about this stuff's probably going to be in the north of Scotland, but we can break it into subzones and give PLEXOS those options. And then likewise for some of the other projects where, again, it's further out and there's more uncertain, we can give it sort of candidate options, candidate nodes, and let PLEXOS do some of the legwork there where it's clearly more uncertain. So basically, it's a bit more specific in the short to medium term where there's reasonable certainty of connection offers in the queue, but later on there's a lot more variability in the locations. So we might, for example, just connect something at a substation, but it's not to say that it will definitely go there because it sits within a wider zone and say, actually, it could move somewhere in there. We're not too worried about the local network. We're more interested in the sort of wider boundary constraints.
So we've got a really good idea of what's happening in 2030. We've created some different scenarios for 2035 and beyond. And this is where that heuristic kind of touchy-feely, let's run that and see what that looks like, those ST runs, we can do that, see what they look like, and then there are points of it that we can optimize. Okay, so choose your onshore wind between these various different subzones. Right, minimize the constraints across that. What does that look like? You've got that amount to do it. So like Paul says, it's a combination of the LT and I'll talk to you about the GSPs because I think we've got a good outcome with them.
Hello, Niall Byrne from Airgrid, the Irish TSO. I'm very curious about what you spoke about, the interaction between the LT and ST. I'm presuming in the ST you're modelling impedance of your circuits, but in the LT you're not. And just if you're not, how much complexity do you think you're losing? How different are the answers between the LT and ST? And if you are, I guess, any tips on how you managed to simplify the LT problem to include it?
So the LT problem at the minute still uses the full network model, but obviously what we need to be very careful of is that problem could get away from you very, very quickly. So what we're tending to do is do some targeted LT runs again on particular years in the first instance to say, there's all the solutions, tell me what 2040 would look like as a single year. Once we've got some intelligence on that one there, we can then say, right, we've got 2030, we've got 2050, 2030, 2040. Let's have a look at the intermediate period and then start to give it a bit of the build out. Because if you gave PLEXOS all the options for all of the circuits for 20 years, we'd still be waiting for it to solve this time next year. So it's trying to get that balance right between targeted runs as well as the automation. And to be honest, we do need to look at the LT settings and see kind of what the optimal is. Wouldn't say we've landed on that as of yet. I think we're still on that journey.
I'm sorry, I've got to wrap it up now, but if any more questions, please find Paul, Lisa at the break. They're here for the next couple of days. We're having a break now. Could we all be back, please, by 3:45? Thank you.
Okay.